So we've already talked about our alkenes as bases. So now what we're going to look at is our alkenes as nucleophiles, which covers this corner here. Okay. Those are what I'm calling the obvious electrophiles to react with them. And then we'll also, in theory, cover these guys, which should be the less obvious electrophiles. And then we'll kind of see where we go from there. Ideally, we'll get into the alkynes, look at where alkynes differ from our alkenes, and then we'll be done. All right, so if you've got the slides, we're probably only getting through 3 or 4 slides. Okay? Just because there's a lot of information on each of those slides. That was supposed to be animated. Here, I don't want the conclusions in there because I want that space. Sorry. I just need space to write. And the conclusions thing is actually a new thing. I did just tag that in there. Okay. So alkenes is nucleophiles. Okay, so what we're looking at is the obvious electrophiles. And what we talked about Wednesday was looking at that first reagent, our BH3. Okay, boron's a special molecule because when we look at its electron configuration or its Lewis structure, we only have 6 electrons around that boron, which means the hybridization of the boron is our geometry is trigonal planar, and what we'd be looking at is an sp2 boron, which means we have an unhybridized p orbital, which is being shown in that last image there. So if we take that boron structure and just kind of rotate it so our hydrogens are in and out of the plane, we can now see that p orbital. Right? That's really nice with the p orbital because what can we do with an empty p orbital? We can put electrons into it. So our boron reagent will act as a really good electrophile, and in that process facilitate all sorts of fun electron transfers and atom shifts around. Okay? So let's take a look at what happens with that. So we're going to take our alkene and we're going to share its electrons with that boron. Okay? And since boron can accept those electrons, we don't have to do any other arrow pushing. That is our single result. And we can draw the result of that reaction. Here's where it's going to get interesting, though. Where do we attach the boron? Which carbon?
Carbon 1.
We got carbon 1, which will help out with red carbon, or carbon 2 is our purple carbon. Red or purple? Okay. Just like our acid-base chemistry. Exact same thing. When we went through and did our acid-base chemistry, what we'd be looking at is leaving a charge. So if we drew the boron on our red carbon, what happened to our purple carbon? It would become positively charged. If we'd attached it to our purple carbon, what happens to our red carbon? Which of those two structures is more stable? Our first one. So what ends up happening? We attach the boron to our first carbon, the red carbon. Okay. This is going to get discussed slightly differently in your textbook. You'll hear a term come out of this, and it's typically referred to as anti-Markovnikov. We'll address that term in just a second. I'm particularly not a fan of that because that just goes based off of what does Markovnikov mean. Instead of that, we can follow the chemistry. Okay, our electrophile is that reactive positive, so let's put it on the most negative carbon. And that is going to be carbon number 1, because if we look at our intermediate structures, we're putting our most stable carbocation on that second position, our secondary versus our primary. Questions about that initial attack? Nothing?
Oh, is a boron in charge?
So no questions on the initial attack, so let's back off and look at our product here. Is there something wrong with our product drawn? We are missing a charge, okay? Our overall charge has to be the same on both the reactant and the product side. And if we look at our reactants, our overall charge is neutral. If we look at our products, our overall charge right now is positive. So we are missing a charge. That charge is the negative, and it is typically associated with the boron. And this is where this chemistry becomes even more interesting. We're saying the boron is negatively charged. Okay? Does boron have an extra pair of electrons that it could donate outwards? No. So it's holding the negative because it is formally charged that way. But where is the actual reactivity within this structure? It's actually out with one of those hydrogens. Okay? And in this case, it's not the reactivity of a hydrogen atom or a hydrogen ion, it's the reactivity of a H minus. Okay? So when this structure goes through and reacts, is we don't get this initial setup. What we'll end up with, okay, I know I just drew that all out, but we'll have our boron, we'll have our hydrogen, we got our other hydrogens out here. Won't worry about those. And what happens is the boron coordinates to the most negative atom, and our hydrogen will coordinate to the most positive. And what we end up with is this four-membered transition state. In that transition state, what's happening? The electrons of our pi bond have come out. Well, let's actually color code that a little bit better. Let's make it blue. Electrons of our pi bond are coming out and coordinating with our boron, making that new bond. Okay, and they came from, I guess we'll show it as a dotted. Boron now has too many electrons and says, I need to get rid of something. Okay, well, hydride is an incredibly horrible leaving group. So it can't just throw it off into the ether and we form that cation. It has to throw it immediately to something that can actually catch it. What can catch it? That forming carbocation. Okay, so we take the electrons out of that old sigma bond and we form to the carbon. And what we end up with is this kind of goofy looking transition state that results in what? That structure.
How do we draw the arrows?
Drawing the arrows, which we're going to start to care less and less about because you won't have to worry about mechanisms per se, is our electrons are going to come out from our pi bond and immediately come, well, I can't even quite draw it on here. We'll come from our pi bond out to the boron, and we'll come from our hydrogen out to our carbon. Okay. So this is happening all at once. Okay, what evidence do we have that it happens all at once? Okay.
The stereochemistry.
We could look at the stereochemistry of our product. If it didn't happen all at once, I've got a carbocation. That carbocation could freely rotate, and I could end up with all sorts of different stereochemistry of the boron and that added hydrogen. What we end up finding is the boron and the hydrogen, it's not easy to see here, are added on the same side of the pi bond. So this addition of that boron structure is a syn addition. Everybody remember syn addition? We did talk about that, right? There are two T's? Doesn't matter. Okay, I like that. Let's do this. Syn addition. Okay? We've added those two things to the same side of the double bond. Does that mean we only end up with one product?
No, that has its enhancement.
We're also going to have the result if the pi bond attacked or interacted with the bottom of the pi bond. Remember, our p orbitals have both a top lobe and a bottom lobe. Every time we do the addition reaction, we run into the possibility of two possible products. With the structure that we've got drawn, do we need to worry about that? No, why not? There's no stereocenter. Okay, so you could go through and actually draw out the other product and say, oh, well, you end up with the same result. Okay? Or you look at the product that you drew. If there's a stereocenter, then yeah, you've got to worry about it. If there's no stereocenter, who cares? Okay? So what we've done is added the boron and the hydrogen across this double bond. Okay, questions about that?
If there's
The relationship could be enantiomers. You can't say they will be enantiomers because it depends on the rest of the structure. Because if the rest of the structure also has a stereocenter that doesn't react, the relationship between your products is diastereomers. All right? So no questions on that addition? When we go through and run this reaction, the boron dumps a hydrogen on. Why? Because boron has a hydrogen. Take a look at our product. Are there still hydrogens on that boron?
Yes.
Can it react again?
Yes.
Absolutely. So what will end up happening is this will react multiple times, and what we'll end up with, I'm just going to abbreviate it, is our boron pretty much having exchanged all of its hydrogens out for now our alkane group coming off the side of it. And this is kind of nice because one reagent allows us to do 3 reactions. How important is that to you for your final test? Probably not that big of a deal. As far as the lab goes, it's actually kind of nice, okay? Because you can use less of that reagent to go through and do this. Okay? How many times have you seen boron in a product? Probably just this once. Okay, fair enough. So we need to get rid of it. Okay, it's not one of our official functional groups, even though we worked with it in this case. So what we'll end up doing is taking the product of this reaction. So our boroalkane structure, that was the result of step 1 of our reaction. And now what we'll do is take that product and react it under step 2 conditions. Okay, so once the boron has reacted, we've given it plenty of time to do its thing. Now we'll go through and take it on to another reaction. Okay, so depending on what we're looking at, this may mean actually isolating the product of that first step, or it may mean just adding it on top of it because we aren't concerned about any side products. Okay, in this case, we aren't concerned about any side products. So what we'll start with in this case is we now have our boron. Let's just draw one of those carbon structures on it. Okay, with our hydrogen on there. And now what we want to do is get rid of that boron. Okay, somehow cleave that off. That's what our peroxide and our hydroxide are there for. Okay? Well, how does that reaction work? That becomes the next fun, tricky question beyond this. Okay? There is an official mechanism, which is actually on the next slide, which I do promise I will post, even though you guys don't have it. Okay? But the mechanism that I prefer to go through and use, just because I think it's easier to work with, is what I'll show you here. Our boron went through and formed that nice 4-membered ring because it could accept electrons. We're right back at that situation. Our boron only has 3 groups, which means it still has that empty p orbital. It can still accept electrons. So what we'll go ahead and do is bring one of our starting materials up near it to see how it could interact. Okay, so we've got hydroxide and we have peroxide. Okay, what is the peroxide going to do? Okay, that could dissociate, get us some radical reactions. So we have a very weak oxygen-oxygen bond in there. So what can happen is our peroxide can start to coordinate to that boron. It can start to share its electrons with the boron. But then what happens to the bond between the oxygen and the oxygen? It cleaves, so what will end up happening is we will shuttle our carbon structure over to it. Okay, horrible, horrible mechanism here, trust me. Okay, but it'll get us to our end result. Our boron is now bound to an OH and 2 R groups, which we could later work with. What happened to our other piece? Oops. Our carbon now has an OH. Oh, kind of cool. So what we've gone through and done was past tense of take our alkene, reacted it with our boron, and in the process have added OH and H across the double bond. So we added water across the double bond. Nice. Does that product actually sound interesting? Okay, and by interesting, is there an easier way we could have done this reaction? I know it was last week, But what else could we react our pi bond with? Okay, if it's not a nucleophile, it's our alkene can't act as an electrophile. So we're looking at the reactivity of our alkenes. It's acting as a base, so let's react it with H+. Where does the H+ go? We'll put our H+ out on the least substituted, so we have the carbocation. And what did we say we could then react that carbocation with? Any kind of nucleophile. The initial reaction, we used a halogen, so we did a hydrohalogenation. Then we went through and changed the halogen from being a halogen to water or an alcohol. If we added water, what happens? Our oxygen acts as a nucleophile, attacks the positive. We'd have a positive charge on our oxygen. Does it want to be positive? So what's it do? It steals electrons from our hydrogen to form our final product, OH, and we get our H+ floating back as a catalyst. Anybody notice anything interesting?
The OH, is that the more substituted carbon?
We've put the OH in a different position. Okay. Why would we want to do that? Well, it depends what drug you're trying to make. Okay. If we want the reactivity out at the primary position, we'd want to use the boron reagent. If I don't care about reactivity being at the primary and I want it down in that secondary or inside the structure, then I can go through and just use acid and water. So depending on what we're trying to get to and where we want that reactivity within our final answer, we may choose different reagents. Okay, we've seen this before. We saw it when we added HBr to the double bond. Okay, if we ran HBr under standard acid-base conditions versus under, that vaguely sounded like someone said it, but maybe it was just random noise, radical reactions. When we did a radical reaction versus our standard acid-base, the bromine went to a different position. What we now have is a way to actually put the OH in a different position as well. Okay? This is where Markovnikov's rule comes up, when we're adding hydrogens across a double bond. Markovnikov went through and noticed that initial reaction at the bottom there and said, well, hydrogen went to the least substituted position. So he came up with, and everybody gave him credit for this cool rule, Markov, close enough. Hydrogen added to least substituted. When we go through and do an addition reaction. What happens with the boron reagent? Where did we put the hydrogen? The most substituted. So it's not Markovnikov's rule in that case. So instead of actually looking at the chemistry and understanding why these things are shifting and what intermediates are produced, we go through and we call that bottom set Markovnikov's rule. What do we call the top set? Anti-Markovnikov. Not to be confused with anti-addition or anti-Newman projections. What we're using the anti for in this case is not Markovnikov. Okay? You may see that name float around. What you should be familiar with is the chemistry that's involved in each of those. Okay? Worst case, just remember your boron puts the OH someplace that you wouldn't have expected. Okay? And that can help you with that reaction. We also talked about syn addition versus anti-addition. If we take a look at where the OH and ultimately the hydrogen, where our hydrogen and the OH were added, where did they end up getting added to? Syn or anti?
They were syn. In
Okay.
the boron.
It is a syn addition, though it's kind of misleading because I just drew it up there. It looked like syn addition. But it is a syn addition because of how the reaction worked. Our boron, when it initially came in, put the boron and the hydrogen where? On the same side of the pi bond. So we had a syn addition. When we go through to look at cleaving the boron off and putting the oxygen on, what happened? Our oxygen, at least the way I've got it nicely drawn here, comes in again from that same side. The stereochemistry cannot change. So we end up with a syn addition with our borane reagent. Okay, so that's kind of a nice little thing to note. That is a popular ACS question. Okay, because it's all dependent on, do you understand how the reaction worked, not just that it put those two pieces on there. So if we were to look at a new question, well, sorry. Any questions about what's up here right now before I show a new problem?
Wait, so how do you know if it's going to be a Markovnikov or not?
So don't look at it as Markovnikov or not. Look at it based on the reagents and how the reagents work. And it's solely based on their intermediates. So that's the issue with Markovnikov or not Markovnikov. How do you know? You memorized it, period. That's it. You had it memorized. If we asked then a syn or anti, understanding Markovnikov is completely useless. Okay? What I'm mentioning is that the Markovnikov term is used because when they first discovered it, they noticed that hydrogen was added to the most substituted position. When we go through and change the reagents, now it looks like, oh, it's anti-Markovnikov. It's the exact same chemistry. What was the positive atom in our Markovnikov addition, the bottom reaction? What was the positive atom that our alkene reacted with? H+. That was our positive atom. Where did the positive atom go? Least substituted atom. What was our positive atom in the case of our boron? Boron. Where did the positive atom go? The least substituted position. If you understand the chemistry, there is no Markovnikov. It's the positive atom goes to the least substituted position, period. Okay? So it's focusing on what chemistry is occurring. When we first talked about this, when adding an acid, what our alkene reacted with was a positively charged hydrogen. The hydrogen went to the least substituted position. Okay? Instead of calling that a rule as hydrogen, call it a rule as the positive. Where does the positive go? Least substituted. When we switch to the boron, where does our positive atom go? Least substituted position, which then means we put the boron at our least substituted position. The next step of the reaction does some odd chemistry that kicks out the boron and puts on an OH. There is no Markovnikov's rule. It's just standard chemistry. Okay, does it make a little bit more sense? Okay. Realize that you'll see Markovnikov pop up. All they're really saying is a positively charged hydrogen goes to the least substituted position. If you change the reaction and it is no longer a hydrogen, what happens to the validity of Markovnikov's rule? It goes out the door, becomes completely useless. So what you need to focus on is not a one narrow specific case, but focus on the chemistry of the reagents present. If you look at an alkene, how do alkenes react? Really important to know. How do they react? What do alkenes have? They have a pi bond. What's in the pi bond? Electrons, which means our alkenes will react as nucleophiles. When do they not act as nucleophiles? They don't. They always act as nucleophiles. Why? Because they have electrons. When does a positive hydrogen act as a positive hydrogen? Only when it's a positive hydrogen. Okay? So, and that's where some of the terminology comes in, becomes a problem. Markovnikov just said hydrogen. Didn't say positively charged hydrogen, he just said hydrogen. So if all of a sudden it looks like the hydrogen's moved to a different position, goes, oh my God, the rules are all changed and everything's messed up. No, you were just focused on the atom, not on the charge, the reactivity of the atoms. Okay? So understand the reactivity of each of the atoms. Look for those charges, because those charges are going to lead you to the answer every single time. Without those charges, you are relying solely on your memorization ability, which, if you're doing that, please have a better memory than me. Okay? Questions? New problem. I'll let you guys sit and work on this one a little bit. What's the product? What's the reaction type? So what type of reaction, looking at those reagents, would we predict to happen here? Sorry? Why would you say addition? So, by saying that we've added hydrogen and OH, actually what you're specifying is the result. You've added H and OH. Okay? That's a bit dicey because you know the reagent, so you're saying, oh, we added. Okay, I want to avoid that. Let's not look at the answer to tell us why it's the answer. How do we know this is? How do we know it's not a substitution?
Because there's no leaving group.
There's no leaving group. How about acid base? There's no acid. We don't have an acidic hydrogen on that alkene, so we can't run just a standard acid-base reaction. BH3 is not an acid, okay, so it can't be acid-base. How about elimination? No leaving group. So it's not acid-base, not substitution, not elimination. Radical? Why can it not be radical? There's no initiator or heat or light. Okay? We could potentially jump in with step 2, but that's step 2. Okay? If we just focus on what we're starting with here. That really leaves us only one reaction. We have to be running an addition reaction. Okay? So when it comes to your ACS exam, just looking at that, you can now start to go through and say, I have to get rid of the double bond. Any answer that keeps that double bond is pretty questionable. Okay? So try and simplify some of the problems first. Try and figure out what steps of the reaction are going to happen, or what types of reactions are happening. The next part, determining the result, that's a little bit trickier. How do we know that we had H and OH? So we know our reagent. Okay? So you still have to know the chemicals involved in each of these reactions. Okay? So if you see the BH3 and THF, you have to know what's happening in that reaction. So you are responsible for having some of these memorized. Sometimes you can get away without the memorization. Sometimes you do need parts of that. What's the result? What we're looking at is a hydroboration. Officially for just step 1 is the hydroboration. Okay, why? Hydro means hydrogen, boration, boron. So in the very first step of this reaction, what do we end up doing? We put a hydrogen and a boron onto it. What's the next step of the reaction? It's an oxidation reaction. We've replaced the boron with an oxygen. Okay? So it's a 2-step process, or a 2-reaction process. When we go through and do our product, okay, we could go back and evaluate the chemistry. Our borons are electrophile, so our positively charged atom needs to go where? The least substituted, which means our hydrogen would go at the other position, and our boron would go on. Okay. Before we even hit same side, deciding syn or anti-addition is going to be dependent on what? If we have a stereocenter. Do we have a stereocenter? Yes. So we must include stereochemistry with our product. Now we have to know if it's a syn or anti-addition. How do we know that? Memorized. Or you go back to the dynamics of how those pieces align. The boron has to sit on top of that. If hydride was kicked out, that is such an incredibly unstable leaving group, it has no way of coming back around and attacking from the backside. Okay, we have to put the hydrogen and the boron on the same side. How do we specify that? We'd need a wedge for both of them. Or we'd need the dash. Okay, officially that means and the dash. In this case, we can get away with saying it's the enantiomer. Why can we get away with saying it's an enantiomer? There's no other stereocenter. If we threw in another stereocenter, it's not an enantiomer. What would you have to do in that case? You'd have to draw the other product out. Okay? That's step 1, or close enough to it. What does step 2 do? Swaps the boron for an OH, and it does it in the exact same position. And what we end up with is our hydrogen and our OH added on the same side of that ring. Both of them are wedged. Plus the enantiomer, both those hydrogen and the OH dashed. 30 minutes, one reaction. Yes. Right on time.
How about the other time?
Were we on time, really?
No,
How
we're
about
not.
this one?
That was already drawn on there. I should have crossed that out. That wasn't there. I was afraid you were going to say that. Okay. Questions? Okay, so let's take a look at the next reaction. Again, obvious is in quotes here. Our next reaction is this mercury species. Mercury's first off is a nasty compound, not particularly pleasant, really toxic. We typically avoid using it just because of its toxicity. Not particularly fun as far as poisoning goes, and not easy to get rid of out of your body. Okay, so we do limit contact with mercury as much as possible. Okay, and that's because it has some goofy chemistry here. Okay, what's the big goofy chemistry that we see within this mercury structure? What do you see on that mercury that might suggest something about its reactivity? Lone pair, I like that. Good eyes. Is that going to be a complication? What is mercury classified as? Metal or non-metal? It's a metal, which means what about its electronegativity? Very, very low. So if we take a look at those bonds between the metal and the non-metal, where do those electrons spend most of their time? On the oxygen. In fact, that's an ionic bond, so we could better look at that structure. Instead of actually with the bonds, we could erase at least one of them. I don't know why I tried to erase like that. I can't erase the structure there. Let's get rid of that. The oxygen would be negatively charged, and the mercury would be positive. Anybody think there's anything interesting with that? We have a positively charged atom with a lone pair. What can the positive act as? An electrophile. What can the lone pair act as? A nucleophile. We have a positive and negative on the exact same atom. Interesting. What do we have in our alkene? We draw a resonance structure. What's our resonance structure show? We have a negative and positive on our alkene. So what can end up happening? We'll take the negative from our alkene and have it attack that positive mercury. Okay, what's going to end up happening is depending on how this mechanism is drawn out. Some people will draw it with the OAC still attached. That mercury now has too many electrons around it, so it has to kick out a pair. So one of those OACs leaves. Okay, so that oxygen takes the electrons with it. Sorry. The abbreviation AC, just for those of you that missed it, this piece here is an AC group, an acetyl group. Okay? So we can kick out that OAC to help kind of make mercury happy, but then it still has that lone pair. What can that lone pair do? It can immediately go back towards the carbocation. The result we seen this before? Those of you in lab at least? Yep. What we actually have is a weird three-membered ring. What's special about this three-membered ring, number one? What can you tell me about this carbon? No, not even to do with electronegativity. Nope, it's not sp2 because of where we started. Stereocenter, which means you need to specify your stereochemistry around that. So let's say that bond is wedged. Somebody did mention we will have the enantiomer option on this too. We will have it also as our mercury being dashed. But the more important part, just say plus minus, what about this other bond?
gotta be wedged.
It will also be wedged. Why?
Because it can't be on the back of one and the front of the other.
Mercury's not going to be able to hit from the top and attach the bottom. That physically just does not work. We'd have to have those bonds aimed the same direction, which means that Mercury is double wedged. All right? What do you guys think? Stable structure or not? Not stable. Is that a good leaving group? Positively charged mercury?
Yeah.
That's a positive charge. It's not particularly a good thing to do. We want to get that mercury its electrons back. So what can happen?
Take the electrons from the bond.
It could take those electrons, but then what do we end up with? We'd end up with a carbocation. Whoops. And which electrons do we take?
Probably from the second carbon too.
Why from the secondary?
Because it can handle the carbocation better.
We have a better or more stable carbocation. So with a really good leaving group, I want to generate the most stable carbocation possible. But as long as that mercury is there, I don't officially have a carbocation. Okay? But what we have identified is a reactive carbon. That carbon is reactive how? Is it positive or negative? Positively charged, which means it wants to react with something negative. Do we have something negative in this step with the mercury? And oxygen coming from, it's not going to be our acetyl. Our acetyl's there typically in very low concentrations. It's coming from the next reagent in that step. Not the next step, but the next reagent. We're also adding that group. You'll notice I've specified it as two things. We'll specify one of them at this instant. We also have water present. Okay, what's going to happen? The lone pairs on the water will attack that position, freeing off our mercury, and what we'd end up with. Sorry, I drew that kind of weird. After we deprotonated, with our alcohol added to our structure. Okay, so we're also following a deprotonation step as well. So deprot, and then we'd move to our product down below. Okay, since the mercury was wedged, our water had to come in from the back side to force that bond to break off. And what we end up with is our trans alignment of our mercury and our OH. Kind of neat. How many times have you seen mercury in a product? This once. So it's not a good thing to have on there. So what's going to happen? Now that we've formed our pseudo-stable intermediate, we're going to react it with another reagent. That other reagent is in step 2, sodium borohydride. Okay. As far as how that mechanism works, that's still up for debate. Okay. The reason why that's going to be important for you, if it's up for debate, can we specify the stereochemistry? No. Oh, that's nice. So what does that sodium borohydride supply? Try again. Try again. Where are the electrons coming from?
From the bond to H.
They took the electrons from the bond.
It's going to take our, if we draw out our Lewis structure, we got this reagent, and the boron is officially negative. Does our boron want to be negative? No, so what happens?
Gets rid of one of the hydrogen.
You got to be careful with your term. It's not getting rid of hydrogen. It's getting rid of hydride. It's getting rid of hydrogen with the electrons. What can those electrons do? They can act as a nucleophile and kick out the mercury. What's the end result? We end up having finally added H and OH across the double bond. Sure, that was fun and exciting. Does that result look familiar? How else could we have made that?
Just by adding H plus and then and OH, or in H plus and water.
That reagent, also seen here with our H plus and water. God, that mechanism was easy. Why on earth would we go through and deal with mercury if we could deal with it just this way? What was one of the intermediates when we looked at the H plus and water reaction? Very first step, what did we form? A carbocation. As soon as you form a carbocation, what should you be thinking about? Stability, which means resonance, and rearrangements. Where's our carbocation in the mercury reaction? Is that in our first step? It's not officially there. That's a resonance structure. Do we ever form the carbocation with the mercury reagent? No. Do we need to worry about rearrangements or resonance? No, because there's never a carbocation present. So exactly as you said, Tim, right at the very beginning, no rearrangements. The mercury reagent is awesome because we don't have to do rearrangements. If we just add H plus and water, we do have the option for rearrangements popping up, and we could end up putting the OH in a position that we didn't actually want. Okay? So let's take a look at an example of that if you're all okay with what's drawn up there.
So you just get a higher yield? Like theoretically?
Yes, it's one way to look at it.
You're not getting unwanted products?
Yeah. So let me cross that guy out again. What if we went through again with our ring, except this time I'm going to put the double bond in a slightly different position. If we go through and run this reaction with just H plus and water, what do we get for a product? We'll end up with a couple products in this case. We need to give you a little time to think about that one. All right. So our reaction type is addition. The result, you add H and OH. So we could go through and specify those in nice capital red. You'll notice that both those positions on the double bond are both secondary, so there really isn't a necessary favoring for a rearrangement in either case, or in one of those cases. But if we formed our intermediate with the carbocation up at that secondary position, what can happen? A rearrangement, and we'd end up with that as our result. Our hydrogen and our OH added across those positions. If we go through with the mercury reagent, sorry, that's an H, we just end up with these two possible products. Between those two, is there one we might suggest as a better one?
The second one.
Okay. I would think that you're probably going to get a slightly better cation, slightly more stable cation here. So we might see something like 55-45 ratio between those two. But we're still going to end up with both. And they're enantiomers.
Because that group's closer to the tertiary.
It's closer to that tertiary group. Yeah, so it's slightly a more stable carbocation. It can pop out a little bit. The mercury can break off there a little bit easier. Okay. So mercury reaction, just to be obnoxious, let's bring back to Markovnikov. What do we end up with? Markovnikov or anti-Markovnikov? It is officially our Markovnikov. We put our hydrogen at our least substituted and our other group at the most substituted position. Why is it a better reagent than running just H plus and water? You don't get that rearrangement option. Hi. Yes.
H plus and water, you have hot water,
H plus in water gives us how many products? 1, 2, 3 products. Plus enantiomers and all that other fun stuff. With our mercury reagent, we end up with both those two and their enantiomer issues. Yes?
Would you still need to show the wedges and dashes?
Officially, yes. When it comes to the actual reactions on what you'd see in a test form, because that second mechanism isn't as clearly known, we're getting a mixture of everything pretty much, so you don't have to stress as much about that. Okay. So that's where our conclusions are. If you see BH3, you see the boron pop up, we've got to be a little bit careful with that statement. We're looking for the OH on our least substituted position, balance the rest out with our hydrogens. We end up with a retention of our stereochemistry in that respect. Retention is kind of a bad term. We'll end up with our syn addition. Okay. If you see mercury popping up, that puts our OH on the most substituted. The big advantage is we don't get a rearrangement. Okay, so those are the big conclusions out of there. I did kind of slip up and say when you see boron, bless you, we just do the OH on the most substituted. Is that always true? We're looking for just boron.
No, because we need boron in the.
It needs to be our borane BH3. Okay, we need that empty p orbital on our boron to be able to have it react as an electrophile. If we take a look at the second reagent in our second reaction, the sodium borohydride reacts entirely differently. And that's because we've put too many electrons on that boron. It's going to dump out a hydride. You're getting rid of that H minus. Okay, so we draw out that Lewis structure once more for both of those. BH3 has what hybridization? sp2. So it has that empty p orbital in which we can dump electrons. BH4 has what hybridization? sp3. It actually has too many electrons. So what sodium borohydride will do, when you see that, just think hydride, H minus. Where would you put that H minus? At the most
At the carbocation.
positive position. Find something positive, slap that hydride on there. Okay. Questions? Yes.
what breaks the bond between the mercury and the oxygen? Make the mercury positive?
To make the mercury positive, so what we're looking at, I've got it highlighted up in red up at the top now. What makes that bond break? We've got multiple options. You can either have the alkene attack. Here, let me just erase everything. If we want to get that bond to break, you can either have the alkene attack, which is going to cause that bond to break, or look at the stability of that product. Is that a stable species? That's actually pretty stable. Why? It is resonance stabilized. That's why when you look at the conjugate acid, acetic acid, how does it typically act? As an acid, because of the conjugate base, this species is really resonance stabilized. It's a stable piece. So it's a good enough leaving group that it can potentially leave on its own. That exact part of the mechanism I've seen drawn both ways. Okay. Don't look too excited. I might think you want to look at more. If you really wanted to look at the boron or the Borane mechanism, in particular with the peroxide, what I showed was a very, very modified version of it. No, it's not in the slides yet. It'll show up later this week. Shows all the individual steps along with that oxidation reaction. You'll notice that it is nowhere near as simple as what I drew. Because I just didn't want to draw it all out. You'll notice in the very first formation, we still end up with, where'd it go? Oh. We'll still start with, before we add the peroxide, the boron with all three alkyl groups, so we got rid of all of our hydrogens. And then what's going to end up happening is we're going to form what's known as the borate ester. Okay? That borate ester is happening because in that peroxide reaction, we actually do some goofy rearrangements, converting our R group onto the oxygen. How do we know this is the valid mechanism and not what I drew? It's a trickier question. Someone went through and actually evaluated all the pieces that were in the reaction mixture. One of those pieces that they found, the trialkyl borate ester. Okay, my mechanism doesn't verify that that's existing. Okay, so we know this method to work truly because that species is actually formed. Okay, the only way we would know that is going through and looking at that reaction mixture and trying to see what happens. Okay, because both my mechanism and this result in the same thing. We get the same stereochemistry in our products. All right? So if you're you're interested in that, you can look at that a little bit closer. What we're going to do is move on to our not obvious electrophiles. All of these are really centering around one, well, almost all of these are centering around one reagent. What's that one reagent in this stack? Br2 with DCM. What is DCM? Dichloromethane, also known as methylene chloride. So it's a methyl group, one carbon with two chlorines attached to it. Okay. So in all of these cases, what we're doing is reacting our standard alkene. Should have adjusted this so we can see an alkene to start with, but we'll pick the same one that we've been working with, our propene. We'll react that propene with each of these reagents. Okay. Where we'll start is at the very top with just our Br2 and DCM. Okay. What's the big difference between DCM, water, and our HOR? Yes, there is a polarity difference. There's another one. What about the reactivity? Water can act as a nucleophile. DCM cannot. So both water and our HOR, also known as an alcohol, can react as nucleophiles. DCM has no nucleophilic ability. Okay, and that's going to change the results coming out of this reaction. Okay, so let's focus on just our Br2 and our alkene. So if we've got our alkene and we have Br2, draw out our Lewis structure for our bromine. How does our alkene act? It's a source of electrons, which means it is a nucleophile or base. Can it act as a base? Why not? There's no acidic hydrogens to react with, so it has to act as a nucleophile. So if it's going to act as a nucleophile, what does it need to react with? An electrophile. What charge does an electrophile have? Positive. Where's our electrophile? Also not really there. And so that's where this reaction becomes a little bit weird. What we found is with our halogens, particularly the larger ones, is that electron density is polarizable. We can push that around a little bit. Okay? We can push it around to the point where that pi bond can share its electrons with the bromine or get near enough to that bromine that what happens to the bond between the bromines? It's going to break. Which way does it break? To the left or to the right? Why to the right? It's trying to get away from the electron source that just came in. Okay, and now we get that bond breaking open. Okay, those of you in lab, this will be the second time you see this, but I want to make sure those of you in lecture that aren't in lab can see what's going on here. If we draw out the results of this, what do we end up with? Where does the other bromine go? Okay, stop saying three thing. You guys are cheating. Those of you that haven't seen it in lab. Okay. We would predict to put the bromine in a position that generates our most stable intermediate. So what we're forming is a carbocation. That carbocation needs to be at the most substituted position, which means we would expect to put the bromine there, okay, at our least substituted position. That gives us a carbocation. As a result of that carbocation, I can now get a free rotation around that sigma bond, okay, and even further, what can then happen for the next step of this reaction? We need to stabilize that positive with negative. What negative do we have? Our bromide. Sorry, I didn't mean to rub that in that much. Came out a little strong. And we'd end up with this as a result. Anybody notice anything problematic with this? We have a stereocenter, which means we would have to specify whether it came in from the top or from the bottom. Okay? So we look back at our carbocation. Is there a preference of top versus bottom? Carbocation, no. We get both products. We would expect it both as a wedge and as a dash. Okay? So someone went through with this theory, probably looked back at somebody else and said, I don't like them, so I'm going to disprove them. So we changed the structure slightly. I'm not sure I'd call it, I'm sure they used the name of science for it instead of saying they don't like them. And if we drop a ring now on the rest of that, what's an added complication by making it a ring? How many stereocenters do we have now? Two. Which means I'm going to have 4 possible products coming out of this, if this mechanism was correct. What if this mechanism was wrong? Then I'd expect to see a different set of products. And I'd probably have to add an extra carbon in here just to make it unsymmetric. Well, someone went through and evaluated and said, well, we don't get 4. We only get 2. And the 2 that we get are these 2. The other ones don't form. If there's a carbocation, they should absolutely be there. What does that mean about the carbocation? No, well, so unstable it's not there. Okay? If it's present, we get the other 2 products. We don't get them at all. So there has to be something wrong with this mechanism. So now people went back to that mechanism, okay, and said that really our issue has to be the carbocation, because that's the only place where we can get this situation coming up, where our 2 bromines are with what respect to each other? Opposite sides of that double bond, trans. Okay, the only way we can get that has to be happening in that last step, because in the first step, we don't have any issues with trans or cis in that case, because there isn't anything to be trans or cis with. So it's all in that second step, which means the carbocation cannot form, period. Not only can it not form, but that other bromide, when it comes in and reacts, has to be coming in from the opposite side from however the other bromine was in there. Okay, so let's make that initial bromine that's on there a wedge. That means our other bromide, when it comes in and attacks, has to come in from the back side. And I'm doing this just to simplify. We still end up with 2 products. Okay, we just end up with this one product in this case, based on this drawing. What does that necessarily mean? What is our wedged bromine doing? It is somehow blocking the other bromide from getting to the top of that cation. Okay? Variety of ways that we could go through and do this. The accepted way that we've evaluated is that we don't form the carbocation. that step doesn't actually strictly occur. The result is that we go to this species. We'll still use that wedged bromine, but instead of it actually floating out there just on its own, that bromine leans just enough to make another bond. Now there's no carbocation. There's no way for the other bromide to attack from the top because there's a bromine already there. It prevents it from getting to that top position. Now, when our other bromide comes up, it has to come in from the backside of that bond, forcing the other bromine to take its electrons and kick out the other direction. That intermediate is what is known as the bromonium ion. I don't know why people laugh at that. I think it's kind of funny. Nice name. I'm going to name my daughter that. I'll just stick with bromonium. Ion will be the middle name. So we're looking, come on, bromonium ion McFadden? It's got a nice ring to it. Just kidding. So what we end up forming is that intermediate. That's going to force the bromines to add on opposite sides of the alkene, and what we've got as a result here would be what is known as an anti-addition. Because the two things that were added to our double bond are added on opposite sides of the double bond. I know, deep sides. Right? We will still end up with enantiomers. Why do we end up with enantiomers? If we look at our very first step, the pi bond attacking the bromine, in that case our bromine was from the top. It could just as easily have been from the bottom, so we do end up with the possibility for even more products coming out of this. All right? Last thing that we want to, well, second to last thing. Let's add that carbon in there. Make that dashed. Okay. What's the result for our product? So we have a very slight tweak to our structure. We now have a methyl group. I want to know where the red bromine is and where the blue bromine is in the product. True, but do I show red up here and blue down here, or do I show it the other way? Actually, let me switch that around. Let's just do it on that same one. Or do I show blue down here and red up here? It's not both.
It's going to be the blue on the lower carbon. Because you're forming a carbocation. Oh no, I'm sorry, it'll be on the upper one because you're forming a carbocation and it's more stable at the tertiary.
All has to do with our leaving group ability in that carbocation. We have a really good leaving group, which means our nucleophile, the bromide, our blue bromine, is going to attack at the most substituted position. Whoops. So let's fix that arrow. We'll have to attack in that situation. Okay? And that's because we have a good leaving group, so we're trying to form the most stable carbocation possible, or pseudo-carbocation possible. Our bromide attacks from that position, which is then going to kick our red bromine to the wedge on our other carbon. Our methyl group will then get pushed forward, and our blue bromide will be dashed going away. With this reagent, is it that big of a deal? No, because they're both bromines. We can't really tell the difference between them. You look at bromine, but it's still a bromine atom. Not going to one magically be blue and one magically red. Where is it going to become more important? What happens in those other reactions? Br2 and H2O. We're still going to have that bromonium intermediate. It's still going to react. I don't like seeing that carbocation up there. I'm going to erase that. Okay. Except now, instead of there being just bromide, I'm also going to have water. Which is more nucleophilic? Bromide's a pretty good nucleophile. It would probably be our preferential nucleophile. So how can we prevent bromide from attacking?
Just low concentration.
We keep it relatively low concentrations, so we dump in a ton of water. Now what ends up happening is our water will act as the nucleophile. Where does the water go? It's going to be in our blue position, which is why we specified with those colors. We'll end up putting our OH at the most substituted position. Can we apply Markovnikov's rule in air quotes to this? What we're talking about is the most positive atom goes where? Least substituted. What was our most positive atom in this reaction? Bromine. Right at the very beginning, the bromine was our electrophile. Where did it go?
Both positions?
Where did it go? It went to the least substituted position. We end up with the exact same result, the exact same chemistry we've seen with all of the others. Okay? So if we can ignore this Markovnikov idea and focus more on the chemistry of those atoms, we can actually start to predict where these positions go and where they're activated. Please feel free to pack up. The last one we'll tag on here is what happens if we add a HOR? What changes? Does not really change the mechanism. All we end up doing is changing the product ever so slightly. Okay? So all three of those reagents are doing the same thing. What I'll leave you guys to think about for Wednesday is what's going on with our hydrogen. Okay? And why do we have to add platinum, palladium, or nickel to our overall reaction? We'll be talking about, what is it, chapter redox? Our redox chapter on Wednesday.